Okay, class, good morning. This is the first lecture for the fall 2020 session of Energy Systems, ELEG 437, 637. And as you can see, life has become a little unusual. I'll make a few comments about the situation we're in. As you can see, I have a little studio set up in my residence where I'll be taping lectures for the class, and that studio, so to speak, includes a blackboard, which I'm only showing a portion here of, and also the ability to project something from the computer on a screen, which right now the screen I have is just poster board, but I'll be getting an actual screen, and hopefully that will improve the resolution of what you can see up here on the screen. And the idea here is that I'm going to try and give lectures on video here that then I can upload to YouTube, and you can view over and over again if you want. And the idea being that to try and get as close to the classroom experience as possible, live classroom experience. So we'll see how it goes. Now, let me just preface the course here by saying that doing this online, it is seemingly becoming quite clear was the right decision by the university due to COVID, and it's not something that I think any of us, including myself, really want, but it was the right decision. So there's no second guessing there. Clearly, we're in a pandemic that requires us to adapt in order to reduce the loss of life as much as possible, and so here we are. Now, we had some email discussion about how to do this online, and decided to do these video lectures followed by class sessions on GroupMe, and hopefully it'll go very smoothly. Now, I think that I might be with a lot of you students here, where doing this creates difficulties in approaching our classes and learning, and doing it effectively. And I'll just say that I'm going to try and approach this with the same enthusiasm I would have if I were doing this in front of all of you in person right now. This course is, I believe, a very important course. It's a course on the future of energy in our society, and it has both near-term and far-term consequences. The near-term consequences are that the field of energy is a great job market, and so one of the goals of this course will be to prepare you to enter that job market. Now, this is an introductory course in the sense that it's a survey course. It provides a broad brush of the field of energy engineering anyway, and so it is a course upon which taking other courses should be based upon, and I hope that you do so. Now, let me see if I can perhaps use the blackboard here. Now, lighting is going to be challenging here because any lighting I put up on the blackboard potentially affects the display, which is hard to see already. But let me see if I can do this and and watch what I'm recording here. So let's start with the purposes of the course and see if I can register this properly. So first of all, I'm getting back used to this from the spring, and I'm going to try and be neat. Today's first class, maybe I'll use to practice getting neat again on the blackboard. But you know, and I'll be watching what I'm doing here. So the first, as I said, is to become energy engineers. And what that means, it's actually fairly simple. And something, you know, you may already have certain knowledge bases for. But the idea is that being an energy engineer means that you're someone who is able to assess an energy situation, whether it be a simple situation like calculating the savings of replacing an incandescent light bulb with an LED light bulb, to vastly more complicated situations like replacing the control system with a pumping system with a variable drive. And you know, the idea behind the course is that you're given enough knowledge and to be able to solve problems like that. You know, as I alluded to, problems like, okay, if you take an electric or take a gasoline-powered car and you want to convert it to an electric car, well, how do you size the battery? Okay, things like that. And so a lot of this is simply learning things like how to deal with units, how to go between typical units of fuel like BTUs per hour and units of electricity like kilowatts. So you'll be learning things like that. And in the past, this section or this purpose or mission of the course was tested in homeworks and midterms. Now, there's been a lot of discussion amongst the faculty and the department about how to handle testing, and it's difficult. The way I'm going to handle this is by increasing the percentage of homeworks on your grade and replacing those with quizzes in class. So the idea is that you know, the reality is that any sort of test, I have to sort of back off and just assume that it's going to be you know, open book. And I don't like the idea of time pressure in a testing situation. And so if I were to give out quote unquote midterms, they would probably be open book and you know, somewhat unlimited time frame or requirement to do them in anyway. And so they're essentially become indistinguishable from a homework anyway. So you know, in the past, homeworks would count for, um, say, you know, 25% of the grade of the course. I think in this case, you know, homeworks are going to count for 45%. Actually, let me revise that a little bit because I got to do the math in my head. 40%. Sorry. All right. Now, that's a lot, and I know there are, because you know I've seen it over the years. There tend to be certain students who don't like doing homework. It's always confused me because you know homework is to me like free throws are in basketball. You don't miss them because there's no reason to miss them. And you know it's the same thing here. Please do the homeworks. You know there's no reason not to. I'm available to help out on homeworks. Of course, it's remote, but we can still deal with that. There's a TA for the course. They can help with homeworks and things like that. And so there's really little reason that homework should be a problem. Now, quizzes then. Well, midterms, there are typically 2 midterms in the course, each one a quarter of the grade, so half the grade with the midterms. And so now the quiz, what will a quiz be? Well, the quiz will be given during class time, during the group meet chat sessions, and they will be relatively simple. It will simply be a check on whether or not you are able to in a just you know quiz situation come up with the right answer. And so quizzes will be well somehow around 35% of the grade. And I still haven't established exactly, you know, how many quizzes there's going to be or things like that. These numbers might be revised a little bit going forward, so you know I'll put that here too. But that's kind of the idea is that you know it's going to be weighted more on the homeworks, less on the quizzes, but not you know substantially so. All right, and you may wonder where the other 25% is going to come from, and you know that leads us to the next purpose of the course. All right, and for that, what I'm going to do first is start going through the syllabus, which you've been seeing up here, and perhaps being able to read as we've been walking through this. Now. So let's walk through the syllabus. There's the first 3 sections you can see here up on the display, and there's first an introduction section, and you know we'll start that in the next lecture. That section it basically is going over what the different forms of energy there are. You know, we'll start with kinetic energy. So you know, if you've taken physics classes, you know we're starting at the beginning here. Kinetic energy, potential energy, and you know the theme is that basically energy is conserved, which you might remember from a physics course. And it can be transferred from one form to another. Sunlight can be transformed into glucose by a plant. And in each stage of transformation, whether it's in nature or in engineering, there are losses. And we can account for where all the energy goes in any system. And so that's the theme there. And so if you go through the sections there, you'll see that there is mathematics involved there. It's relatively simple mathematics, but you know, we'll be going through it. Now, after that, we you know, and in that section, you know, we'll talk about, you know, we just alluded to that sunlight um, uh, represents power, and we'll go through, make sure we understand the difference between energy and power. And so as sunlight falls on a plant, it is that power, which we can quantify in kilowatts, is converted into essentially chemical energy. And so chemical energy is a form of potential energy, in that it's stored, and we can think of it that way, and we can then you know, start to make calculations based upon that. Now, so I'm going to come back here because it sort of helps to first look at this chart I've put up. Now, and I know you can't read this in the video here, but and I apologize for this multimedia form of mine and its deficiencies, but the idea is that as you're watching this video, you're also able to, you know, whether in print form or on a separate window on your computer screen or something, be able to look at the course notes and so be able to read them accurately here. Now, this chart shows the U.S. The energy is called flows, or how we get energy and how we use energy in the United States in the year 2019. And it's showing various colored boxes on the left here, and we'll start at the bottom because, you know, that tends to still be the largest box in this chart. That's petroleum, and we all sort of kind of know roughly what petroleum is. Petroleum is, you know, like gasoline, and you know, that represents the largest source of our energy, and basically it's a form of chemical energy that's that we mine from the earth in the form of, you know, oil. And there's other boxes here. You know, biomass is kind of okay. Let's focus on these three here: petroleum, coal, and natural gas. So those represent the largest sources of our energy, and then these other ones are smaller, and you can see that based on the size of the bars here. So you know, right now we still get 80–85% of our energy from those sources: coal, petroleum, and natural gas. And so in this section, we are going to talk about where our energy comes from. And you can see the first section here is chemical energy mined from the earth: oil, coal, and natural gas, and cover, you know, where that comes from, how you know, how we obtain it, how we refine it. We'll get into how we use it also, and go from there. Now, let me skip on to number 2 here let me skip to number 3 and go back to our chart here. So if you can read separately on your course file, this box here is nuclear. We all kind of know what nuclear power is. Of course, you'll know more about it as you go through this course. And the, that's this section here. And, I'm sorry, this, this section here too, nuclear energy mined from the Earth. Now, let's look at 1 and 2 here, and sort of think about it from a very high level first. This chemical energy mined from the Earth, oil, coal, and natural gas. Well, we have direct physical experience with that. I mean, if you drive a car, every time you go to the gas station and fill up with gas, you are directly experiencing, this source of energy. Now, where did it come from? Well, we'll establish in this course that that energy came from sunlight. It was converted by plants eons ago into chemical energy that the plant wanted first, glucose, and then when those plants died, they fell down and formed layers of plant matter that over eons was converted into one of these 3 forms. And so, the ultimate source of these 3 was sunlight, tens or, well, ones or hundreds of millions of years ago. And we'll establish that. And you can see again, going back to the first introductory section, that one of the teaching themes I want to impart in this course is that I want you to understand where energy comes from and how it goes into another form. And the idea is that that will help you understand things like, okay, where can we get energy in the future? So number 2 here, okay, currently nuclear energy, and when we go through nuclear energy, we'll talk about nuclear fusion a little bit, but it's primarily, I mean, at least well, 100% really, is basically uranium used in fission nuclear power plants today. And where did that energy come from? Well, just 1 second, sorry. That energy we'll show came from when in stellar events prior to the formation of our solar system, lighter nuclei were caused to fuse together and create heavy nuclei, essentially uranium, and other heavy nuclei. And so the energy came from things like supernova events and things like that. So the idea is you understand, okay, energy comes from someplace. It comes from some event or set of events that occurred that allowed energy to be converted from one form to another, and then basically stored in the earth in the form of uranium, or stored in the earth in the form of oil. And if you count, A, B, C, and number 2 here, that's, kind of well over 90% of our energy comes from these things that we dig up out of the ground and have figured out how to convert back into something useful, like driving a car. Now, then, if you look at this chart, there are some different boxes here. There's solar energy. There's also hydroelectric. There's wind. Geothermal kind of is in this state by itself, and then there's biomass. Biomass to a certain extent is the same as these three, only current biomass, as opposed to something that's been processed over eons in the earth. So where did they come from? Well, I mean, obviously, kind of, they come currently from the sun. And this one is obvious. I mean, most of this are solar panels, which is one of the things you'll learn how they work in this course. And so there's a direct conversion from current solar energy to electricity in this box. Hydroelectric power is essentially solar energy in the sense that, I mean, it occurs because the sunlight causes water to evaporate and form clouds and then be elevated in reservoirs that we can then tap that gravitationally potential energy. Wind, same thing. I mean, wind energy comes from the fact that the sun heats the earth and causes air movement. And of course, biomass, that's growing things in the sun. And so when you look at this section here in sources, you can see this number 4 is all grouped together in the solar energy, which includes wind and hydroelectric and solar panels and biomass and things like that. And you can kind of roughly divide things into the sections 1, 2, and 3 being stored energy in the earth that has been stored there over eons, and number 4 being our current form of energy that we derive on a daily basis from the sun. And you can make philosophical comparisons that 1, 2, and 3 represent you can make the analogy that 1, 2, and 3 represent mankind's inheritance, so to speak, what we have inherited from the millions of years that have occurred before we've been on this planet. And number 4 is our current sort of income, so to speak. It's what the sun can produce for us right now on a daily basis and what we can utilize. And you can see in the chart based upon the thickness of these lines, wind, hydroelectric, solar, and biomass, that they're very much thinner than these lines for petroleum and coal and natural gas and nuclear. And so you can just see, one of the things that you see directly from this chart is that we're still living off of our inheritance, energy-wise, to a large extent. And these lines, solar and primarily solar and wind, hydroelectric doesn't change much. They are getting larger, but still represent a small percentage of our energy utilization. Now, that sort of leads us to, or points to, you'll see that there's this section D here under chemical energy mined from the earth. And that's there because while I don't think you can say that a realizable goal of this course is to determine this, because no one can determine this. What we can do in this course is we can at least illustrate the phenomena, which is that particularly these 3, oil, coal, and natural gas, are being depleted. I mean, in a very global sense, right? You can kind of understand that there's a finite amount of this stuff in the earth that we can mine up, and we're going to run out of it someday, and the only question is when. Now, like I said, it's very difficult to try and model it or in some way determine when it's going to run out. Um, what you can do is you can illustrate what happens, um, which is you can illustrate, what the length of time an oil well will produce oil, um, which is on the order of years. Um, you can sort of use geology to try and estimate, well, how much of it is there and how much can be accessed. The idea here is that I can't provide for you a number in years that these forms of energy will be still available. But I can sort of illustrate to you that it's probably not more than 100 years. And so, what that means is that when are things like that going to happen? Well, pretty far away in terms of our own human experience, which is on the order of years, but pretty close in terms of our experience, as a species, which has undergone thousands of years. That we're going to have to move away from these, and that sort of is naturally happening, and perhaps even happening the way it's supposed to be. But the idea is that we want to try to come to grips with this and understand what's happening and how we can recognize the effects of it. Now this one here, uranium. Okay, well, first of all, there's other sources of nuclear energy, other ways those stellar events, billions of years ago, stored energy in the form of heavy nuclei. There is nuclear fusion. We'll talk about that too. But one of the things we're going to show in this course is that uranium pretty much, depending on how you look at it, is not being depleted. And so one of the messages of the course is that if we want to, we can rely upon this source of energy being present for a long time to come if we want to. Now, having sort of prefaced that, we can get to the second purpose of the course, which is your final project. And that final project is essentially to reproduce this chart. And I think this year we'll do it for 2050. So now you're not going to draw. This chart will be rendered into an Excel file, and it's actually kind of fun. The final project, you put in numbers. You put in numbers for how much of our electricity will come from wind in the year 2050, and how much will come from nuclear power in the year 2050. How much coal we'll use. Things like that. And the final project is and again I may be revising these numbers a little bit, but in the past it's been 25% of the grade. It's an unusual final project, so to speak, for an engineering course, because there's kind of no right answer. Actually, there was a way to get wrong answers and not adding up right things, but I sort of fixed that in the file, so you can't not add up right. I mean, we haven't covered over here how currently gasoline powers something like 95% of our cars, and you can't see it. You can't see it on the screen here, but if you look at your file, there's this little tiny line here, which is, you know, how many of our cars are electric, and you'll be asked to determine, you know, what that is in the year 2050. Now, depending on your answer there, you have to come up with electrical sources, you know, and things like that. Now, you can't make that mistake in the file unless you really try hard. So it's not like you can make a wrong answer. You can make the numbers look similar to the way they are today. The final project, and we'll go over it more and more as we go through the course, is meant to illustrate how well you are able to think about this subject and come up with reasonable answers to questions. So we'll talk about that more as we go through, but you can see that the sort of two aims of the course here, which is, you know, on the one part, to try and become experts in the sense of understanding what the future holds in terms of energy for particularly the United States, because, you know, if we tried to do the entire world, it would be too complicated. And then number one, which is to try and be able to solve these, you know, energy-related problems, like, you know, how much a leaking hot water faucet is costing and things like that. All right, and as part of both of them, and I didn't bring it up for today because you know, I wanted to keep this first lecture very high level on what the course is about. You know, starting for the next lecture, we'll get into a lot more details and things like that. But part of both 1 and 2 are to be able to evaluate new things in the energy area that are coming online. I was reading yesterday an article about a new form of sort of essentially electrolysis, sunlight electrolysis, where these scientists had produced a device that converted sunlight into chemical energy. And you know, the idea is that once you take this course, you can read an article like that and ask intelligent questions, which, you know, intelligent questions are, you know, okay, what was the conversion efficiency? And, you know, that would be very easy to figure out if you were actually someone doing it, and the fact that it, you know, wasn't there in the article meant that there was something a little suspicious going on. But in any event, the idea is that you are armed with the knowledge and understanding in order to evaluate things. And for example, if you become an energy engineer, okay, and let's say, you know, 5 years from now, you're working as the corporate sustainability engineer, and you know, for, I don't know, some large company, and your job is to evaluate ways for the company to save energy. And some vendor comes to you with some widget that says that, well, if you implement this widget in your systems, it will save you 20% off your electric bill. And, you know, so you have to be able to perform an engineering scientific analysis of that claim. So, you know, that folds into both 1 and 2 here. You have to be able to use the knowledge from this course to evaluate whether that claim holds any water or not, or at the very least, to be able to ask the right questions for that vendor as to how they established that 20% number. So, you know, that's extremely important, right? I mean, you know, your job could depend in the future on being able to do that. All right, so let's sort of move on here a little bit and talk about the final project a little bit more in terms of what it is not. And so I'm going to shift gears a little bit here, and you'll recognize that up till now, the focus has been energy. The focus has been, okay, we utilize energy in our society, and as energy engineers, our job is to make sure that this system works wherever it needs to work. If the job could be making the conversion efficiency of gasoline into motive force better, engine technology. The job could be making better wind turbines. Okay, making them more efficient. Okay, so wherever it is, okay, you were able to make this chart work better. Now, what's been missing from that discussion so far, and what I always discuss briefly at the introductory lecture of the course, is global warming. Your final project is not meant to be affected or taking into account global warming. Now, the reason for that is not because global warming is not something we need to be concerned about. It's just the fact of the matter is that that would introduce a sort of undefinable complication, in the sense that global warming, as we'll see in a minute, is because as we utilize these sources here, we emit CO2 into the atmosphere, and at least that's the primary source of global warming. And so if we, the problem is that if we said to ourselves, okay, you're going to make your final chart for 2050 addressing global warming, well, you'd have to eliminate all these. And some could argue that that's possible by the year 2050, but it would just sort of, it would make the project probably unrealistic. Now, that's something we can talk about and think about, but and maybe during the Group Me session tomorrow we can discuss it. But let's talk about global warming for just a little bit, so we know what's going on at least. Oh, by the way, this chart here, this chart is actually meant to start to address the depletion of petroleum. This is our global. These dots here are our global production and consumption. When you dig up petroleum out of the ground, you can store a little bit of it, but I mean there's very little storage, and so of the sort of 85 million barrels of petroleum dug up out of the ground every day, all of it goes into all of it is essentially burned that day. After going through some minor storage. So this represents both consumption and production. And what this chart is showing is that this black curve here is exponential growth at 1.29% per year, which is what you would kind of expect to be happening in a unconstrained situation. And the actual is a little slower than that. Now, whether that means that we're starting to see the early effects of depletion is not clear, but it's simply data and that we can talk about. All right. So global warming, and global warming is primarily the beginning discussions in terms of this chart here, which shows the prehistoric record of average global temperature and CO2 levels. This one here this is not temperature. This is the difference from an average temperature over time. You can see this is the present, well, this is, 300 years ago. And then 50,000 years ago, back out to 400,000 years ago. And you can see that over that prehistoric time record, the global temperature fluctuating. And this is, over that same time period, the CO2 levels, which went between 200 parts per million and roughly about 280 parts per million. And you can see that there's this kind of rough correlation that when temperatures were higher, CO2 levels were higher. So there's this is the way, this is the Al Gore chart. This is the way that to anyone unversed in the physics of infrared absorption in the atmosphere, the point is made that increased CO2 levels will lead to increased temperature. Now, that's true, by the way, and it has become well verified even today. And I guess I'm not sure how much detail I want to get into here, but well, let's just walk through it. So this is an updated chart that I updated last week, and you can see it in your notes. This is the source. Every year at this site, NOAA puts out what the average CO2 levels were for that year, including 2019 now, that point there. This is a semi-log chart. I'm sorry, this is the year, so 1750 to 2050, and we're here around 2020, 2019. The preceding charts so you can see the CO2 level chart here. That's quote-unquote the present day, and it's at around 280 parts per million. That's actually, that corresponds to this position around 1750 here, around 280 parts per million. So that's where the two charts meet with each other. Now, what you can see is that those time scales shown above, that whole chart was 400,000 years. This chart is roughly 300 years. So compression by a factor of 1,000 or so. And you can see how, now again, this is a semi-log plot. So a straight line on this plot represents exponential growth. And you can see how, in the 1800s, we were seeing a slight rise. It was rising at a very slight rate. And then around 1950, it started really taking off. And then, it's been increasing from there. And the main point of this chart, is that each of these straight lines, if you're familiar with a semi-log plot, represents an exponential. If this was a linear plot, this would be, out of the roof by now. And the point of the chart is that the slope of these lines has been getting larger itself. Now, what does that mean? There's been no slowdown of CO2 levels in the atmosphere. In fact, there's been an acceleration. And I started teaching this course around 2006. and you can see that that acceleration has been continuous the whole time and unabated. And I've been sort of interested to see whether it slows down ever, and it does not. Now, you can see then that based upon our current rate, by the year 2050, we'll be approaching 500 parts per million. And if we go back to this chart here, you can see that you know, these are ice ages, you know, when it's low like this. And the difference between an ice age and a warming period like human civilization has been in is roughly 80 parts per million. All right, now over here, I kind of don't want to do this because it changes the focus of the camera. But if I were to go over here, those last 300 years, you know, would be like a little, I mean, this would be up now projected by the year 2050 to be at 500. So the difference between our, you know, climate we've been accustomed to in an ice age is 80 parts per million. And now we're going to be 500 minus 280, we're going to be 220 parts per million above that. So it's extraordinarily dramatic. Now, you may ask yourself, if 80 parts per million in the prehistoric record resulted in, and this is Celsius, you know, a 10 degree Celsius change. All right, well, 220, I mean, I can just do the math, times 220 over 80, that should result in, you know, like, I don't know, a huge temperature change. Well, so what's going on? Well, I mean, it takes a long time. There's some discussion in the notes, but if you compare these two charts, there's about an 800 year, which you can't really see on this scale, time lag between one and the other. And the Earth is a big place, and so, you know, from the prehistoric record, it takes hundreds of years for the effect of changes in either temperature or CO2 to have an effect on the other. So, you know, that means that, you know, whereas these changes in CO2 have occurred over the last 20, 30 years, that their effect will be taking place hundreds of years into the future. And that's, you know, very dramatic. And so the answer is that, you know, right now, at this very moment in time, you know, global temperatures are higher than they have been. You have to be careful whether you talk about Celsius or Fahrenheit, but a few degrees, either one, and you know, that's going to continue. So should that, okay, so a lot of students ask me when I teach this course, okay, well, shouldn't that be our main focus then? Okay, shouldn't this final project be all about that? Okay, because obviously this is an enormous problem, and we have to be doing something about it. And I'll just say that, well, that's true. And you know, every semester, you know, I'm open to discussion as to whether we want to revise what that final project is. The purpose of the final project as it exists, though, is not necessarily so much to be an accurate prediction of the future, but an exercise into what is possible. And so the reason why I'm going to resist any changes to it is because I want you to see, okay, which you will see from the final project, that if, for example, you projected in the year 2050, 80% of our vehicles will be electric, okay, you will see then, okay, how that impacts all of our sources of energy in terms of coming up with that electricity to power those electric vehicles and things like that. So the name of the course is Energy Systems, and that's what the final project is. You are to recognize the systematic effects of the choices that you make. So, my intention is to keep the final project as it is, which is that as you make your choices, they won't be based upon global warming. They'll be based upon engineering and roughly understanding what is possible and what the effects of the various choices are. And again, it's a little bit different of a final project for an engineering course because there's not necessarily any right or wrong answer. It's in how you explain your answers. All right, so getting back to global warming, I'm happy to have discussions of it offline, so to speak, and we can talk about what's happening and what may happen. It should be recognized that it is an existential threat to humanity. And so now, what may happen in the future? Well, it doesn't look, I mean, you can see a few charts here, and that going to the upshot here. That's an old chart. I mean, I'm not a climate scientist, and so I made this chart up many years ago and haven't tried to revise it or anything because it's sort of a curve fit. It's not really, it's a somewhat sophisticated curve fit, but it tries to represent what the time lag of global warming is, and over the years it has turned out to be relatively accurate in the sense that it predicts, by the year 2050, somewhere close to a 3-degree average Celsius increase in average global temperature, and by the year 2100, around a 5-degree. And those numbers tend to continue to be supported by climate science. So, the sort of back of the envelope calculation, over the coming century has not looked, has looked right. Now, the issue is that, again, one concept is that that won't stop then. And going hundreds of years into the future, this temperature rise will continue. And yeah, I mean that sounds pretty horrific. I mean, because even at a 5-degree rise, it is catastrophic to our society. And if 100 years from then it's 9 degrees Celsius, then that's more than catastrophic. Let's just put it that way. Now, does that mean we have no hope? No, it doesn't at all. It means that that as engineers and scientists, we have our work cut out for us. And right now, okay, what we can do is we can try and reduce the amount of CO2 being emitted to the atmosphere through wise choices in how we consume, what energy sources we use and how we use them, and try to limit the slope of this curve. Um, Beyond that, you know, uh, 100, 200 years in the future, certainly I would expect that one of the main engineering challenges in the year 2100 will be to remove CO2 from the atmosphere, which, is happening right now. There's active scientific and engineering projects on how to artificially remove CO2 from the atmosphere. Of course, we know the plants do it, and we will explain that. That's going to continue, and if this curve is followed, I mean, certainly you can expect that by the later half of this century, that will be one of the primary activities, primary technological activities of mankind. And sorry, that was my cat. One of the things we're going to be dealing with as we go through the semester are my two cats and their involvement here. But anyway, the point is that we to a certain extent, we as a society, based upon our choices of energy and how we use them, have established ourselves on this path. And it's like anything else in human experience, is not something to be to be completely resigned to. I mean, because as I said, I well expect that science and engineering will prevail in the future and cause this curve to be altered by removing CO2 from the atmosphere. Okay, so that sort of is the introduction to the course. I hope it was entertaining and informative. And in the next lecture, we'll start with sort of the scientific meat of the course, and as mentioned, we're going to be talking about energy. Okay, what it is, how it gets converted, how it gets utilized in different forms, etc. And just prefacing the next lecture, this is the primary equation I want you to be familiar with. Energy is force times distance. We're going to start with that. And so logistics. All right. You can see that this course benefits from a multimedia presentation, and for today's lecture, the solution has been to project the course notes at the same time that I'm able to write on the blackboard, mimicking the classroom. But it just is it will turn out probably that there will be lectures like the next lecture where I'll try to just do it completely on the blackboard and refer to the course notes. So this is sort of evolving, the logistics here and how I handle the presentation. Feedback is appreciated. Again, I've never lost enthusiasm. I've been teaching this course since 2006. I've been enthusiastic about it the whole time. I will mention that I run an extensive energy efficiency program, and I look for students to join that program from this course. So it's very important to me, and I'm going to make every effort to make it work for you as well. Okay, that's it for today.